So when we talk about absorption and reflection, we can set up this ratio called albedo, where we have the total scatter power over the total incident power. And so a higher albedo means that there's a greater amount of light scattered. So for instance, snow has a very high albedo because the scatter power here is much higher than, for instance, like charcoal. If so, the incident power on charcoal, the light coming in, most of it's absorbed. Hardly any of it's reflected. That's why the albedo is so low. And for snow, it's very, very high. Now, we'll also still need this relationship here, right? If you take power and spread it out over an area, you get what the intensity is. And so that's helpful there. All right, so we'll try this sample problem here. Light flashes on a metal surface. The surface is 0.4 meters by 0.35 meters, and the intensity is 75 lux. Lux is a watt per meter squared. It's the unit, though, for intensity of light. So just like in sound, we had a watt per meter squared. There's no special unit for intensity of sound, but for light, we use lux. And we want to find out the surface's albedo. So go ahead and pause the clip and give this a try, and then when you're ready to check, you can hit play to continue. Okay, so we should get for our area 0.14 meters. We can get the incident power. The incident power is 10.5 watts. For the scattered power, we get a power of 9.8 watts. And we'll set up the ratio there. We get a albedo of 0.93. Now, what you may have done is just, put 70 lux, 70 watts per meter squared over 75, right? Watts per meter squared. Now, incident power over, or scattered power over an incident power, remember what power is, right? So, power divided by area is intensity. So intensity times area equals power, right? So if you did that, what you did essentially was you did IA over IA, where the areas canceled out, and then you just did intensity over intensity, and you got the same thing. But as you think through this and you work through this, make sure you recognize that's what you did. You just can't throw those two numbers over each other, and do that. You have to recognize, it's power over area. All right, so this is a picture of a solar panel. It's important to understand the difference between this and a solar cell. Solar panels heat up water by, light coming in, hitting the surface, and water is actually ducted through here and then back out, and that light hits it and warms it up. So here's another picture of that where you have the cold water coming in here, and as it goes through, right, you have the sunlight coming down, hitting it, and it's absorbed, and then the water going out is warmer. Here's some pictures of some solar panels on top of some, looks like a retreat center or something like that. All right, so this is O11, and we have the intensity of the sun, and this one is 950. We have a solar panel that's 3 meters squared. It's 45% efficient. First, I want you to calculate the useful power, and then next, if you had 15 minutes and you had 10 kilograms of water in there, how much would the temperature increase? So go ahead and pause the clip and give this a try, and then when you're ready to check, you can hit play to continue. All right. So we've got the intensity, we've got the area there, and we end up getting a power of 2850, but it's only 45% efficient, right? So we multiply that by 0.45, and we've got 900 seconds. So the effective energy over that 900 seconds is this value here. MC delta T, right? We can find the increase in temperature. The specific heat of water is 4186. We have the mass. We know how much heat is going into it, so it's going to increase in temperature by 27.6 degrees Celsius. Now, solar cells convert sunlight into electricity. They're about 30% efficient. They're great for remote areas, warning lights that are away from electricity, water pumps for farms, a lot of good use, potential use for them. And, some advantages, again, they're free. The fuel is free, right? We get the sunlight, it's inexhaustible, and it's clean. Some disadvantages, and these are significant, right? It only works during the day. If you have cloudy weather, it does not work well. Low power output overall, right? And so you need a lot of area to be able to do this, and the initial cost is high. Okay, so when we take a look at this situation here, we have energy coming from the sun, and as light spreads out, it spreads out spherically, just like sound did. So the light is spreading out, and the sun is radiating 3.9 times 10 to the 26 joules per second. That's watts of energy it's sending out. And the Earth is an average distance of 15 times 10 to the 10th meters from the sun. And so what we want to find out is what is the intensity of the light when it reaches us here on Earth. So go ahead and calculate that out. And if you forgot, the surface area of the sphere is 4 pi r squared, so that's how the intensities or how the power is going to be spreading out. So go ahead and calculate that, and when you're ready to check, you can hit play to continue. All right, so we've got our power divided by 4 pi r squared. We'll get an intensity of 1379.3 watts per meter squared, and that's what would. So if you think about how that light is hitting Earth, right? It's only hitting a part of the Earth. And as it hits the Earth, it's got to spread out around it kind of spherically there, right? So, the radius of the Earth is 6,400 kilometers approximately. And, only half of the Earth is exposed. And so if we estimate essentially what hits the Earth, right, we could approximate, essentially a sphere, right, with the light coming in and a circle of light coming in. And so that circle, right, is going to spread out over the sphere of the Earth here. So pi r squared, we're dealing with this area here. And so, if we were dealing with the whole this much power, that's essentially how much power is hitting the Earth. Now, what's interesting about this is without the atmosphere, the Earth's temperature would be about 18 degrees Celsius, which is far too cold, negative 18 rather, which is far too cold. So we have the greenhouse gases that are needed to be able to keep the Earth's temperature where it needs to be. So let's take a look at this here. The solar constant is S. For Earth, it's about 1,400 watts per meter squared. So if we take, intensities power over area, the solar constant would be power over area if we consider that. And so power equals the surface, or S, the constant, solar constant, times the area. And the albedo for Earth is low for water and forests, and so mostly absorption there. But it's very high for albedo. The albedo is high for snow, desert, and cloudy areas where the light bounces off. So the average albedo for the Earth is about 0.3. And so if we consider that, right, and we have pi r squared, which is the area, we can get, and we know the albedo of the Earth, right? So we can place that in there, 1 minus the albedo times the solar constant times pi r squared will give us the power. And so if we look at that, 0.3 in there, we get about 70% of the incident rays. And so, 30% is reflected right out. So what we also have to consider here is, how is that power spread out? And so, we have the surface area of the Earth, 4 pi r squared. However, with the light coming in, we'll have to consider that. So dividing the surface area of this, we can get the intensity, the average intensity on the Earth. And so that'll cancel out there. And so we're dealing with about, the average intensity. And let's go ahead and calculate that, right? So we're getting about 1/4 of it, right, as we work through that. So if we think of the Earth's energy balance, the Earth radiates out what it receives evenly, and we can find the average temperature of the Earth. And so, what it receives, it radiates out, and so the Earth, there's a balance there. This Earth is surrounded by space, 0 Kelvin, so we'll assume that the Earth is a perfect black body. And if this is what we have coming in, and this is what we have going out, we can divide by area to get this value. And so what's coming in should equal what's coming out there. So if we know that's true, if these are equal, we can find the average temperature of the Earth. And we'll subtract those out, and we get, the average there, -17. Okay. So if we consider back with Wayne's law, what kind of light is coming in, we know that the Earth is radiating out infrared. We're receiving a lot of visible light. We're also receiving ultraviolet and infrared as well. So that's important to consider as we move forward here. One of the simulators that I'd like for you to look at if you missed today's lesson, or for using this as a take-home lesson, is to go to this simulation and go to where you have the molecules with the greenhouse gases. And what you'll see are these depiction of these molecules, and then you'll have light coming in, and then you can describe what's happening. And this is a really big part of our discussion here. So if we take a look at this diagram, right, we have the sunlight coming in. This is the Sankey diagram, so all these columns are proportional to what they actually, represent. So, the sunlight's coming in, and some of it, gets reflected off the sun. Some of it actually gets reflected off the surface. Some of the light is coming in and hits and is received. Some of it's absorbed by the atmosphere. And then if you look at what's happening with the Earth, right, the Earth is radiating out a lot of infrared. Now, those greenhouse gases absorb infrared. And so some of them, get absorbed and then they're sent back to Earth. Some of them make it into space, right? Some of the greenhouse gases themselves, after they absorb it, send it to space. And so, without the greenhouse gases, right, we would